Today, I want to talk a little bit about trigonometric substitutions. So this section is linked very closely to 8.3. So there's a lot of the stuff that you do in 8.3 will come back in 8.4. So those powers of trig functions will be what you end up with after doing your trigonometric substitution. So a lot of those will come back into it. So I want to go through a couple of these and sort of talk about it a little bit. So we're going to talk about using the Pythagorean identities again. So this time we need all of the Pythagorean identities. So last time I believe we just used like the 1 minus cosine squared or a few of these other ones. So this time we want to make sure we know all of them. All the Pythagorean identities come from the very first one. So sine squared of x plus cosine squared of x equals 1. From there, I can get all the rest of these. So I can solve for cosine squared in my equation, and I get cosine squared is 1 minus sine squared. I can solve for sine squared. Again, sine squared is 1 minus cosine squared of x. Then if I divide everything in this by cosine squared of x, I get sine squared over cosine squared is tangent squared of x. Cosine squared over cosine squared is 1, and 1 over cosine squared x is secant squared x. So that gives me another Pythagorean identity, and then I again can just use this to solve for tangent squared or solve for secant squared, or get secant squared minus tangent squared is 1. Same thing for cosecant squared. This time I divide by sine squared of x. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. 1 over sine squared is cosecant squared. So I can use that identity as well. All right, so now the idea will be there are certain things that I cannot integrate. So in particular, I cannot integrate the square root of a squared minus x squared. So if I'm trying to integrate this thing, you'll notice I really would like to do a u substitution where u is a squared minus x squared, but du will have an x in it, and there's no x outside of the square root here to take the place and take part in this du, and so it just doesn't work to take this this substitution. And so I say, okay, so I can't actually do that. So instead, I will make another kind of substitution. What I'm going to do is I'm going to make a trigonometric substitution, meaning I'm going to let x be a trig function, and that will allow me to make the substitution work. So in particular here, if I substitute x equals a sine theta in for x in this square root of a squared minus x squared. So anytime I have a squared minus x squared, this is the substitution that I want to end up getting, as long as it's something I cannot integrate. So I make the substitution. When I do this substitution, you'll notice this is a little different than all the other substitutions I've done. So all the other ones I've said u equals something in terms of x. Well, here I've said x is something in terms of theta. So what I need to do is go backwards and figure out what theta is, theta in terms of x. So I solve for theta in this equation. I divide both sides by a, I get x over a, take the inverse sine of both sides, and that will give me my theta. So theta is the inverse sine of x over a. And so that's where we go with it. Okay. Now, what does that do for me? So I make my substitution. I let x equal a sine theta. That's going to be squared. So that is just a squared sine squared theta. I can factor an a squared out of both terms here. So that comes out in front. And I'm left with 1 minus sine squared theta in there. Well, what was 1 minus sine squared theta? Well, according to this, 1 minus sine squared theta is cosine squared theta. So what can I do with that? So that means I can replace 1 minus sine squared theta with cosine squared theta. And you'll see the advantage of this, right? So the advantage of this is now I've turned this thing that was a sum of two things into a perfect square, or a difference in this case of two things. It turns into a perfect square, which is great. That's great news for us, because now the square root of that is just the absolute value of a cosine theta. Now you have to do an absolute value here, just to be really careful. That cosine, it could be negative or it could be positive, but when I take the square root of the square, I always get a positive number back out. So you have to have that absolute value on there. Most of the time when you're doing an integral like this, you're integrating with respect to x, and that x, those x values give you theta values that are between sort of 0 and pi over 2, or maybe even negative pi over 2 and positive pi over 2, because those two quadrants in your plane here are going to have cosine be being positive. So remember, it's all students take calculus is the mnemonic for this. All of the trig functions are positive in quadrant 1. In quadrant 2, only sine is positive and secant or cosecant is positive. In quadrant 3, only tangent and cotangent are positive. And in quadrant 4, only cosine and secant are positive. All the other ones are negative in those. So where we're looking for this is we're going to be integrating in either quadrant 1 or quadrant 4 or a mix of the two. And so we normally can drop that absolute value sign. So if that's the case, we drop the absolute value. If it's not the case, then I have to make those things where the cosine is negative, I have to make them positive by taking a negative of what I get for that integral. Okay. Cool. So let's try an example of this. So I have a circle, radius a. I want to write it as an integral, and I want to find the area. Now, the area of this circle, we already know, right? So it's a circle, a radius a. So the area is just pi r squared. And so in the end of all of this, if we do this right, we should get pi times a squared as the area of this circle. Okay, so that's nice. At least we know where we're aiming. So at this point, we're going to do some stuff. We're going to do this trigonometric substitution. We're going to try it and see if it works. And if it works, I should get pi a squared out of it. Okay, so I know the area of the thing I'm trying to get. I could write it as an integral between two curves because a circle, we have to remind ourselves, the equation of a circle is x squared plus y squared equals r squared. And r in this case is a, so it's x squared plus y squared equals a squared. And so then I can solve for one of my two variables here. So it's either y is plus or minus a squared minus x squared, or x is plus or minus square root of a squared minus y squared. So one of those two I'm going to do. So I'm going to do the y. So solve for y. What I get is two bounding curves, a top one and a bottom one. And this is not a circle, obviously, but it should be, right? So this should be a circle, just sort of not going to be drawn very well by me. That's all right. So what I have here is a top curve. That's the square root of a squared minus x squared. And I have a bottom curve, and that bottom curve is the negative square root of a squared minus x squared. And so I could do that integral, but what we get out of this is sort of a difference of two functions, right? So I take the top one minus the bottom one. And so my integral ends up being like 2 times the square root of a squared minus x squared. And that's not really very helpful to me because, again, that doesn't really introduce a new x or introduce something that makes it easy to integrate this. So what I want to do instead is I want to even go like pare this down even more. This is a circle. And so I want to take the top of this circle. And if I wanted to, I could even just sort of erase the bottom and just say twice the top is going to be the area of the circle. So twice the area of the top function is the circle. Or even better, maybe even more convenient, is a quarter of this integral times 4. And so if I integrate from 0 out to a, the top function, and then multiply that by 4, what I should get is the area of the circle. And so at the end of all of this, I should get pi a squared if I've done my integral correctly. Okay, so let's set up that integral. So what does that integral look like? Well, it looks like 4 times the integral of square root of a squared minus x squared between 0 and a. That's 1/4 of the circle. It's that top quarter of the circle on the right. And what's nice about this is that all of those are in quadrant 1. So we're sort of maybe working a little bit here of magic, but basically I want to do that because if it's all in quadrant 1, cosine is positive in that quadrant. I don't have to worry about absolute value in the end of all this square root stuff. And so that's what I'll do. I'm going to take all this stuff in quadrant 1, take 4 times that area to get the total area of the circle that I'm interested in. All right. So now what do I do? So now apparently what I was supposed to do is make a substitution. And the substitution I want to make, in here is that x is a times sine theta, which means that theta is the inverse sine of x over a. Okay, so we kind of go for there. And I'll make that substitution. Dx is just going to be a times cosine of theta d theta. So I want to get everything in terms of d theta there. And so that's where I would go with this. So I make my substitution. The nice thing with this substitution is it directly just plugs everything in to my equation here. So what I get is this whole thing is just 4 times the integral of the square root of a squared minus a squared sine squared theta. So I square x. Outside of my integral, I have dx. dx is a cosine theta d theta. Now I need to do a little bit of thinking. I need to find my limits of integration. So to find the limits of integration, I plug x equals 0 and x equal a into this equation with this inverse sign. And the great thing here is that this works out nicely because a seems tricky, but when I do this with my theta, theta evaluated at 0. So when x is 0, I'm taking the inverse sine of 0 over a, and 0 divided by a is 0, and the inverse sine of the angle 0 is 0. Or sorry, the inverse sine of 0 is the angle 0. So remember, inverse sine says what angle gives me this as my sine. And now theta of 1, or sorry, of a, so the top of this integral is the inverse sine of a divided by a. A divided by a is 1. So I get inverse sine of 1. And inverse sine of 1 is just pi over 2. So the angle that gives me 1 when I take the sine is pi over 2. Sine of pi over 2 is 1. So pi over 2 is the inverse sine of 1. Okay, so my two values here are 0 and pi over 2. And we can already see the kind of magic that happens here. That is going to introduce a pi in my equation. And I need a pi in my equation. So I need this equation, this integral, to end up being, well, pi r squared over 4. So pi a squared over 4. So somehow this is going to introduce the right thing for us. And this is great. This is really nice. So what do we get? So we try this again. So let's kind of keep working here. So what I need to do is I need to evaluate my a squared minus a squared sine squared. I'm going to factor out the a squared. And then I'm going to integrate from there. So we're going to take our integral here, and I'm just going to go ahead and clear this all. I'm looking at 4 times the integral from 0 to pi over 2, the square root of a squared, and I've got 1 minus sine squared theta inside, times a times cosine theta d theta outside. 1 minus sine squared theta is cosine squared theta, so I get 4, the integral from 0 to pi over 2, the square root of a squared times cosine squared theta times a cosine theta d theta outside of the square root. And this is awesome. So what this gives me, I take the square root of a squared cosine squared, I get the absolute value of a cosine theta. A is the radius, so it's positive. Cosine of theta is positive between 0 and pi over 2. So I can drop my absolute value sign, and what I really get here is the 4 times the integral from 0 to pi over 2 of a cosine theta times a cosine theta d theta. Well, that's great. A times a is a squared. So integral from 0 to pi over 2. I have a squared. Cosine times cosine is cosine squared theta. Now we go back to that previous section. So in the previous section, how did I integrate cosine squared of x, or cosine squared of x in that case? Yeah. So just to integrate cosine squared of a, I have 4 out front, I'm going to take the a squared out, the integral from 0 to pi over 2, and I have cosine squared theta inside. Cosine squared theta, using the half angle formula, is 1 plus cosine of 2 theta all over 2, integrate with respect to theta. And that's going to work out for us. So now what do we get? So now I can integrate this whole thing, and I'm going to separate it into pieces. So I'm going to pull 1/2 in front. So I'm going to get 4a squared. I'm going to have the integral 0 to pi over 2 of 1/2 d theta. So that's the first two in this fraction. And notice I can split the fraction because it's a sum in the numerator. I cannot split a sum in the denominator. So if I have a sum in the denominator, it does not split up, but a sum in the numerator does split up. So that's sort of a nice thing here. So I have 1/2, and then I have plus the integral from 0 to 2 pi, or to pi over 2, excuse me, not 2 pi, pi over 2, of cosine of 2 theta over 2 d theta. And that 4a squared is multiplied by that whole sum there. So I can integrate the first one really easily. What I get is 4a squared, and then I get a theta over 2 evaluated between 0 and pi over 2. Plus, now I can integrate this one as well. So the antiderivative of cosine is sine of 2 theta over that 2 theta is like a u substitution, has to introduce an extra 2 in the denominator. So that's a 4. And then I have that evaluated between 0 and pi over 2. So we're almost done here. Evaluating this, and that 4a squared is times that whole thing. So evaluating this, I put pi over 2 into the numerator. Pi over 2 is pi over 4. So this whole thing is 4. I get a squared and pi over 4. Plus the sine of 2 times pi over 2 is the sine of pi. The sine of pi is 0. And the sine of 0 is 0. That actually is not in there anymore. And what do I get? I cancel my 4s. I get this whole thing is equal to pi r squared, pi a squared in this case, right? So that's great news. That means we did it right. We got something that we expected to get out of that. Okay. So overall here, what we got was the right thing. It was just pi a squared. So that's good. So we made that substitution. That's the substitution we make anytime I have a squared minus x squared inside of something. If I have a squared plus x squared inside, I'm going to make the substitution x equals a tangent theta. And that means theta is the inverse tangent of x over a. And why do I do that? So I go back to my Pythagorean identities here. X squared plus 1, tangent squared of x plus 1 is secant squared. And so what I'm looking at here, if I make this substitution with x equals a tangent squared, I get a squared plus a squared tangent squared x, or tangent squared theta. I can factor an a squared out. It's 1 plus tangent squared theta. That 1 plus tangent squared theta becomes secant squared theta. And the derivative of tangent is secant squared. And so when I do my substitution, I'll introduce an extra secant squared as well. So I kind of have a nice everything's got secants in it. And so once I have everything with secants in it, then I've got powers of secant and tangent potentially that I then can use the material from 8.3 to integrate that. And so we sort of have that ability. All right. And then the last one we want to talk about for forms is x squared minus a squared. This is a little bit different than the first one. The first one was a squared minus x squared. So you have to make sure you know which one you're doing. If I have the x first, I need to do the substitution a secant theta. And the reason is we're going to end up with something minus 1, secant squared minus 1, instead of 1 minus something squared. So if it's a minus x squared, I'm going to do a sign to make it turn into cosine. If it's an x squared minus a, I need to do a secant. So I end up with a secant squared minus 1. So that's the big trick there. And so here I'm going to end up getting the same sort of substitution, and it never hurts to see it more than once. So I get a secant theta, and I'm squaring it, minus a squared. That's going to give me a squared secant squared theta minus a squared. I factor an a squared out. I get secant squared theta minus 1. That's going to become a squared tangent squared theta. And this one, again, it turns into a tangent. And then I have the derivative of secant has a secant tangent. So what I have is powers of secant and tangent, and we use the stuff from 8.3 to then go through and integrate that. Okay. So I want to try one of these. So what I have here is I have an x squared minus a squared. And a here is 16. So if you didn't know that, you can take the square root of 256. Square root of 256 is 16. So that's great. So this is really x squared minus 16 squared. So the substitution that I want to make is that x is 16 times secant theta. And that's going to be it. So that means dx is 16. The derivative of secant is secant theta tangent theta. And what is theta? Theta will be equal to the inverse secant of x over 16. So again, I can go through this formula right here and solve for that. Divide by 16, take the inverse secant of both sides. Theta will be inverse secant of x over 16. Then we go from there. This becomes important at the end. So when I do my substitution, I do the substitution, I do all the integration, and then I end up with something in terms of theta. At the end of all of that, I need to go back to x. So what I will have to do is use this theta in terms of x to go backwards to back to x from here. Okay. So let's try it. So let's make the substitution. So I go ahead and make the substitution. What do I get? I get 1 over, it's going to be 256 times secant squared theta minus 256 raised to the 3/2 power in the denominator. And then times the dx, well, the dx is 16 secant theta tangent theta d theta. And so what I do is I put the 16 secant theta tangent theta on top, and then the d theta comes outside of that. So now what? So now I take my 256, and that's times secant squared minus 1. And that's all raised to the 3/2 power. And this is nice. The 3/2 power is the square root raised to the 3rd power. So I can do the square root of this and then take it to the 3rd power. And that's what I would end up with out of this. So we can go from there. Now, secant squared theta minus 1. Based on our Pythagorean identity, that is just going to be tangent squared theta. Okay. And I think, if I've done this, I believe I have all this in here. So I have 16 secant theta, it becomes 16 secant theta, tangent theta, d theta. Theta is secant inverse of x over theta. Oops, that should be x over 16. My apologies. That should be a 16 down there. And what do I end up with there? Now, I make my substitution. It turns into my tangent squared theta on the bottom, and it's in the 3/2 power. So the square root of this will be 16 tangent theta, raised to the 3rd power is 16 cubed tangent cubed theta. And then I can cancel a 16, one of the 16s gives me a 16 squared in the bottom, one of the tangents in the bottom gives me a tangent squared in the bottom, and then I have a secant theta on the top. And so now what do we do? So now we need to integrate that. And what I would do is replace everything with sine and cosine, just to make life a little bit easier. So what do I get? So secant theta is 1 over cosine theta. So I get 1 over cosine theta. Tangent theta is sine squared theta over cosine squared theta. And then 16 squared stays 16 squared. The cosine squared goes on top. This cosine goes on the bottom. And so I am left with cosine squared of theta on top, sine squared times cosine theta on the bottom with a 256 on the top. The cosines will cancel. I get cosine over sine squared. And so then that gives me what I need. Now I have two choices here. I can do a substitution with u equals sine of x, and then I'll end up with a 1 over u squared, and then I can integrate. Or actually, the choice that I would make is I would notice that I have cosine of theta over sine of theta times 1 over sine of theta. Theta's in the bottom, is equal to cotangent theta cosecant theta. And the antiderivative of cosecant cotangent is negative cosecant theta. And so I can actually do that antiderivative without having to do anything else. So what I get is just a negative cosecant theta over 256. Now we need to do a bit of work. What is it I need to do? I need to use trigonometry using the fact that the inverse secant of x over 16 is theta. So I draw a right triangle. The angle of interest is the theta. And I know that secant of that angle, which is the hypotenuse over the adjacent, so secant is hypotenuse over adjacent, should be x over 16. Okay, so what I am doing here is that this angle, theta, when I take the secant, should have secant equal to x over 16. Now I can find that third side. The third side is just going to be the square root of x squared minus 16 squared, or 256 in this case. Okay, and now I want cosecant. So what is the cosecant of an angle? The cosecant of an angle is the hypotenuse over the opposite. So remember, cosecant is 1 over sine, and sine is opposite over hypotenuse. So I just flip that, make it hypotenuse over opposite. So the cosecant of theta is going to be x over the square root of x squared minus 256. And that's all over 256 plus c. When I have two denominators like this, I can just slide this denominator in here. So I end up with just negative x over 256 times the square root of x squared minus 256 plus c. So that plus c is like outside of all of that. Okay. Cool. So this one is sort of the most trig that we're going to end up needing to get here. And so what I end up with is just that. And then I have a plus c at the end. Okay. So there's only 7 questions on this sort of 8.4 homework, but they're all going to take you a little bit of time, and they're all kind of tricky with the substitution. So you just have to do a little bit of work, write down a lot of what you do as you're going through it to get it to work. Cool. So I'm going to let you go do that now. So go try that homework. Let me know if you have questions. Certainly email me. Certainly come into my office hours if you need to. And absolutely email me and let me know that you want to meet as well if you want a time outside of office hours to meet. I can always sort of accommodate most times. So thanks so much. We will see you next recording.